We can continue our discussion of electrostatic forces by talking about what's called the electric potential energy and use that in the discussion to talk about what's called the potential difference. Well, the first term we understand from last semester, Physics 141, energy. We talked about different forms of energy last semester. We talked about kinetic energy and gravitational potential energy and spring potential energy. So potential energy basically is the ability to do work. So as I take this marker and lift it against Earth's gravity pull downward, I'm increasing the gravitational potential energy of this marker. If you remember, gravitational potential energy was equal to the mass of this marker, m, times the acceleration due to gravity, which is g, times the height of the marker, h. So as I increase h, I increase the gravitational potential energy of this marker. That's due to the fact that I'm moving this marker against the force of gravity trying to pull it down. Now, when you place a free charge, in this case, let's pretend the charge is positive, in an electric field, you accelerate that charge because it's free to move. It feels an electrostatic force from the electric field. We talked about that in the last video, or last set of videos. So the electric field puts an electrostatic force on this charged particle. That force causes an acceleration, right? F equals ma. Force equals mass times acceleration. If you place an unbalanced force on an object, you accelerate that object. If you accelerate the object, you're changing its velocity. Changing the velocity, namely changing the speed of the object, changes the object's kinetic energy. The simple example of that is as I drop this marker, right? It speeds up. The force of gravity is accelerating this marker, giving it kinetic energy. So gravitational potential energy turns into kinetic energy. Now I've drawn this setup to be in the same direction, hopefully, so you can connect the two types of forces more directly. Here we have a plate. It can be a conductor or an insulator, it doesn't matter. We're positive charge. It has excess positive charge on that plate. On this bottom plate, there's excess negative charge. Now, when I place a free charge, in this case a positive charge, in between these plates, all of the positive charge on the plate above pushes down on this free positive charge because like charges repel. All of the negative charge pulls down on that positive charge because unlike charges attract. So this charge is going to feel an electrostatic force downward. Now in green, I've drawn the electric field lines for this setup. This setup is often called a parallel plate capacitor, and we'll talk more about that later in the videos in this lesson. But the electric field lines originating at positive, terminating at negative charges, in this case going straight down, uniform electric field between these plates. When I place an unbalanced or a free charge, a plus Q in this electric field, there's an electrostatic force downward, like gravity is downward. Now, of course, I could reorient these plates and have the electrostatic force be upwards or to the right or to the left, whatever direction I want. But I wanted to go downward so you could more easily see the analogy with gravity. Now, the force experienced on this particle, this charged particle, will cause that particle to accelerate downward. That acceleration will increase the kinetic energy of the particle. But that energy has to come from somewhere, right? Energy cannot be created nor destroyed. That's talked about conservation of mechanical energy again last semester. In the case of gravity, its gravitational potential energy turns into kinetic energy. Here, its electric potential energy turns into kinetic energy. One way you can think about this is it's almost like a spring, right? If you take this free particle and free charge and you can grab it, imagine grabbing it and then lifting it up. There's a resistance there. It doesn't want to be closer to the positive plate. It wants to be closer to the negative plate because that's how electrostatic forces work. So you'll get resistance as you pull this up, and then when you let it go, it will fly down. It's almost like you're storing energy, or not almost like it is. You are storing energy and then releasing it. Now, if this were a negative charge, the same thing is true. The only difference is the negative charge wants to go up and not down. So if I let a negative charge go, it would fly upwards rather than moving down like a positive charge in this example. Now, gravity has nothing to do with any of this. I'm talking about the electrostatic forces on this particle. I'm not worried about gravity at this point. So, the change in kinetic energy has to come from somewhere. Well, it comes from the negative change in potential energy, and a little subscript E means the electrostatic potential energy. And of course, that's kinetic energy related to potential energy. And then there's the work potential energy theorem, which we talked about last semester. The work done on a particle is equal to the positive change in kinetic energy or the negative change in potential energy. And a work means that a force is applied through some distance. So work is done by the electrostatic force, right? Work equals force times distance, again from last semester. So the electrostatic force, when placed through some distance, means work is done. This work changes the electrostatic potential energy. But the amount of electrostatic potential energy there depends on a couple of things, right? Depends on the strength of the electric field, which will determine the strength of the force, right? The change in gravitational potential energy depends on the work. Work is equal to force times distance for a constant force. And we're going to pretend that this force is constant for the time being. The force depends upon the electric field strength and the charge on the particle, right? So this is going to be equal to Q times E times D. So the work done, which is related to the electrostatic potential energy, depends upon the charge Q, depends upon the electric field strength, and depends upon the displacement, how far you move, or how far it moves. But note the charge, right? I would like to talk about what's going on here without using this charge. Because the charge could be anything. It could be positive 1 coulomb or 10 coulombs or a tenth of a coulomb or a billionth of a coulomb or negative 1/millionth of a coulomb or negative 1 coulomb or whatever. I would like to talk about this system in a way where I'm not bringing in the charge on of the point particle, this test charge. This is very similar to when we talked about electric fields versus electric forces, right? The only difference between the electric field and the electric force here, the electric field, is that charge Q. The force, you have to worry about the charge Q. The electric field, you don't have to worry about the value of the test charge. I want to talk about this system. I want to talk about electric potential energy in similar terms. I want to talk about it without worrying about the value of the test charge. And let's look at what happens when we do that. Since the electrostatic potential energy depends upon the test charge, the value of the test charge that you have in the electric field, we want to introduce a new term or definition that ignores that value for the test charge. So we introduce basically a concept. We want to have the electric potential energy per unit charge, right? We want to divide out that test charge value. So the electric potential energy per unit charge has a specific name in physics, and it's called the electric potential. And it's usually labeled by a capital V. So the electric potential is distinct from the electric potential energy. Electric potential energy has SI units of joules. Electric potential has SI units of volts. So the electric potential is the electrostatic potential energy divided by the value of the test charge. Now this is nice because, as in the electric field and the electrostatic force, the relationship between those two is simply multiplied by the test charge. This is the same way. So if I told you the electric potential between 2 points, you could tell me how much energy a charge value Q gains just by multiplying that charge by the electric potential, right? Rearrange this equation, multiply both sides by Q, you get the potential energy is equal to V times Q. Potential is used a lot more in electric circuits than electric potential energy. So we'll be using this electric potential, or your book will start referring it to just as potential, far more often. And again, the units of electric potential, or just potential, is that of volts. You've probably heard of that unit before, right? A 9-volt battery, for instance. Most of you know what a 9-volt battery is, or a 12-volt car battery, or AA battery, which is 1.5 volts. You already use the terms of electric potential in everyday speech. So, for example, a 9-volt battery, that means there's a potential difference of 9 volts between those 2 little terminals on the top of the battery. How much energy does one electron gain from moving from one of those terminals to the other? You can actually calculate that. You know the electric potential is 9 volts. You know the charge on an electron is minus 1.602 times 10 to the minus 19 coulombs. You can multiply that and tell me what the electric potential energy is in joules. Now, joules, unfortunately, is really a big unit, right? Joules is appropriate for measuring energy of a freight train flying by, or a car, or a person, right? It's a useful energy on a macroscopic scale. But when we're talking about accelerating these tiny charges, like electrons and protons and things like that, joules is too unwieldy, right? It's too big. It's like trying to measure, the mass of paper or the mass of a fly and use tons. You can tell me what the mass of a fly is in tons, it's just not a very useful unit. So we actually introduce a more appropriate unit of energy at this time. Your book talks about the electron volt. So the electron volt, substitute EV, small e, big V, that's the unit. It is a unit of energy. It is equal to 1 electron volt is 1.602 times 10 to the minus 19 joules. So you can see it's a much, 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 much smaller unit of energy. And we will learn when we start talking about transitions of electrons in atoms, the electron volt is an appropriate unit of energy. For example, to completely ionize a hydrogen atom, we will learn, to completely rip the electron off of a hydrogen atom takes 13.6 electron volts of energy. Now, a couple of confusing things that you will get tripped up on that I hope to clear up now. The first is the electric potential, the symbol for electric potential is a capital V. But volts also have units, right? It's a capital V. So you'll get answers where it will look like the electric potential V is equal to 12 volts. So you'll get something that looks like V is equal to 12V. And from a math point of view, that makes little sense, unless V is 0. But remember, one of these is a variable, the potential. The other is just a unit. So it might be helpful is whenever you come across volts, spell it out. So there's less confusion between electric potential, the symbol for electric potential, and the symbol for volts. The second confusing thing that you'll get tripped up on is the electron volt. Even though the word volt is in the unit, it is not an electric potential. Electron volt is an energy, right? It's equal to some sort of number of joules. So you can convert joules to electron volts and electron volts to joules. You cannot convert joules to volts. They're different units. It's like saying I'm going to convert centimeters into seconds. It makes no sense. So there's two things you can possibly get tripped up on. So be cautious when you're solving these types of problems.